Good afternoon, everyone. So the topic of my presentation this afternoon is on remote sensing and the work that we've been doing using these different technologies for detecting and monitoring red needlecast. So the bulk of the research that we've been doing is around the use of Sentinel-2. Just a quick recap, Sentinel-2, it's a constellation of 2 satellites operated by the European Space Agency. It's got pretty decent resolution, 10-meter spatial resolution, very high spectral resolution. But importantly, it's got a 5-day revisit time. So every 5 days, we get free imagery for the whole of New Zealand made available by the European Space Agency. But I also want to take the opportunity this afternoon to present how we've been integrating a range of different technologies. So we haven't just been using satellite-based methods. We've also been using things like UAVs and traditional aerial platforms to try and work more closely with the forest health researchers and try and integrate some of these technologies into the work that they're doing. So we recently completed a Levy-funded project where we looked specifically at using Sentinel-2 data for detecting and monitoring red needlecast, and the goal was that this data is free and we can potentially turn this into some sort of a platform for large-scale detection and monitoring using the Sentinel-2 data. But in order to do that, we had to take a really deep dive into this data, and we had to do a lot of validation work on both the data that comes off the satellite and how to process it as well. So what we did was we took all of those key findings and we decided we'd roll them into a bonus additional tech note called Sentinel-2 Technical and Practical Notes for Forest Managers. And the goal of that tech note is to do exactly that. It's to try and break down the barriers for forest managers to use this rich data source that's now available. So the sorts of topics we addressed, well, we looked at things like how does one go about correcting for terrain? So what we found there was you're effectively limited to 90-meter resolution terrain correction. And what you can see in the panel on the far right-hand side there, panel D, you get these wavy artifacts that are introduced into the imagery when we try and use, say, for example, our LiDAR DTMs that we're catching there at the same time. We also addressed a range of other topics. So we looked at things like what is the best method for atmospheric correction. We tried a range of different atmospheric processes. And it's probably lost on the overhead there, but it makes a pretty substantial difference. So at the bottom there in the center, we can see that our choice of atmospheric correction really makes a difference in terms of the haze reduction. We also looked at what's the best way of masking out clouds from this imagery automatically. There's a huge range of cloud masking algorithms out there. And what you can see is that in the top there, the image on the left is the European Space Agency's suggested method of detecting clouds. But we actually found the results, at least over forested areas, were slightly better when you chose a different algorithm. That's also fairly easy to implement there at the same time. We also looked at some very practical topics. So how do you get the data? It's obviously fairly easy to go to the website and download imagery, but we wanted to try and break down the barriers to integrating this on a routine use of this data within the forest companies. So we provided examples on how you might script the operation so that you can download this data from something like Amazon Web Services automatically. And then we also gave script examples on how you might form up queries so that you can talk directly to the European Space Agency's servers and tell them, I want cloud-free tiles or tiles with less than 30% cloud for this particular area covering my forest, and I want them from the date I last acquired them to the most current imagery available in the archive. So we tried to come up with a range of sort of use cases to try and help automate the acquisition of this data for forest managers. Then lastly, the final thing we looked at was some very sort of technical details on how to get these tools up and running. So the European Space Agency, they make a lot of processing tools available. But they require some configuration, and some of it's fairly technical. So in this report, we give you technical examples of how to get these things set up. But then we also decided to do some basic analysis, and we ran through how would you do this in tools that are already widely used in the forestry sector. So things like QGIS, or how do you work with the Sentinel-2 imagery and ArcGIS, which almost everybody has and uses in the sector. So the goal of this work was really to try and break down those barriers. As Phil said this morning, I am one of those scientists that really wants to see this used, and I really want to see increasing uptake. This is a phenomenally rich data source, and the European Space Agency have a long-term commitment. They're already designing the next series of Sentinel-2 satellites. So I think that we have an opportunity here to take this data and start using it in our forest operations. And I encourage you to get hold of the report, and please feel free to send me any queries. I really hope that I can help you to take advantage of this data source. But we haven't just been looking at Sentinel-2 data. We've been looking at a range of different remote sensing technologies to try and assist with things like detecting and monitoring red needlecast. So the image here on the left is from a UAV. So what we're looking at there is this very high resolution RGB imagery. And on the right-hand side of that panel, you can see the multispectral equivalent of that, again captured off a UAV. And what this shows us here is that these new technologies allow us to characterize the disease expression right down to the level of the individual tree. That's something that would have been very hard previously. And when you throw in things like multispectral imagery there, it becomes even easier to identify the scale and location, of the disease outbreak and the symptoms. We've also been trying some slightly more experimental approaches. So we take this high-resolution RGB imagery and we fuse it with the structure from motion point clouds and with our LiDAR data as well. And then because we've got that LiDAR data, we can drape these point clouds over the terrain, and we can fly through the canopy surface and identify the pockets that have been severely affected by red needle cast, and we can locate them in the landscape. And we hope that that information is valuable to the forest pathologists in terms of figuring out what drives the expression of the disease. But of course, if we have LiDAR, the first question that any forester asks is, well, what is red needle cast doing to my LiDAR that I'm collecting for my K nearest neighbor yield imputations? So we explored this as well, and the first thing we went after were gap fraction proxy metrics, or metrics, LiDAR metrics that capture the rate of pulse penetration through the canopy. And you can see that the figure on the left-hand side there shows an area that's quite severely affected by red needle cast. The interesting thing is that the figure next door shows a much simpler LiDAR metric. It's just the median height of all LiDAR returns, and the red needle cast really stands out there, the areas that are quite severely affected by red needle cast. So the next thing we did was we did a paired plot analysis. So this is where we take areas that are quite severely affected by red needle cast and then comparable areas that are less affected, and we look at the distribution of LiDAR returns in those paired plots. And what we see is a substantial shift in the distribution of the returns. So from those two histograms there, on the left-hand side, on an unaffected stand, lots more LiDAR returns are captured in the upper canopy. Once they've been severely defoliated by red needle cast, as you would expect, those LiDAR returns are just passing directly through the upper canopy, and they're collecting now in the understory and on the ground returns as well. And so the short answer is, yeah, this disease is impacting the LiDAR that we're collecting, and it is having an impact on the metrics that we're generating from this data. So earlier on, Stuart showed a really interesting figure where he showed the pathologist's view of the disease cycle. But at the same time, thanks to the advent of Sentinel-2 and the fact that it's been collecting data for some years now, we're able to develop the remote sensing equivalent of this. And it's slightly delayed, and it's a little bit of a lag from what Stuart showed, and our working hypothesis is as follows. So what you can see here on the upper left-hand side is the 22nd of November, we're looking at an area of forest that's quite severely affected by red needle cast. There's a lot of brown foliage, and our reasoning is that it's still sitting on the tree. So the needles have not yet been fully cast, and there's a lot of this material on the trees, and that's being reflected back to the satellite. But by February, those needles have been cast, needle extension is complete, and so what we see is a greening of the forest again. By April and May, in addition to the forest growth, we're also starting to see understory flush as that moisture stress is released, and there's virtually no evidence of the red needle cast. But come August and October again, it's in full bloom, and we can start to see the signs of severe red needle cast outbreak in the forest. The really interesting thing here is that the pattern seems to have shifted. So some of the areas that were worst affected in the previous year seem to be slightly less affected, most likely because we're running out of healthy needles to infect, and new areas are being quite severely hit by the red needle cast. And again, this very clear pattern continues. So by November, it seems to have peaked. February, many of the symptoms have disappeared from, at least from the satellite-based observation. March and May, moisture stress is released, and the symptoms have basically disappeared again. The key thing is we don't have to do this just using visual interpretation. This also shows up in our vegetation indices. So these are indices that are quite closely related to canopy health. We screened over 200 different vegetation indices looking for which one was going to be best for detecting and monitoring red needle cast, and we arrived at RV, Atmospherically Resistant Vegetation Index, and it really highlights the trend here again. November, very clear signs of the disease, but by May, RV is essentially saturated out again as the canopy and understory have begun to recover, and so the cycle repeats again and again. But the key takeaway here is that we've got this very clear cyclical pattern that we can detect using Sentinel-2 data. So we've got this phenomenal data source that's going to be collecting imagery over New Zealand for the foreseeable future, and we can detect red needle cast, and there's a pattern there as well. So the next logical step is for us to try and develop a statistical approach to automatically detect and monitor red needle cast. So at the moment, we're currently looking at evaluating two different methods. Both of them have been trialed in the US. The first is where we do a seasonal regression. So we collect data from just a particular season, say always summer. We fit a regression, and then we look for substantial deviations from that trend line going forwards. But a much more appealing but slightly more complex approach is that we do things like fit a harmonic regression. So here what we do is we try and capture two patterns. We capture that seasonal pattern in the changes of the forest phenology, but we capture a broader pattern as well, which is the forest canopy growing and maturing over time, and so we end up with a general increase in whatever the spectral vegetation index we're looking at over time there as well. And that gives us two opportunities to look for deviations from this harmonic regression. And it also lets us capture that additional data with the in-season observations, because instead of looking at just every summer, we could now take 4 observations, 1 per season per year. So the question is it likely to work in New Zealand? Well, we've only got 3 years of data from Sentinel-2, so it's a little bit difficult to fit a convincing regression to 3 data points, but that didn't stop us trying. And so what we did was we picked out some areas in the forest that were quite severely affected by red needlecast, and we grabbed all of the RV values for all the pixels that were within those affected and unaffected areas. And what this figure shows here is there's a substantial deviation when we look at that time series imagery. So it looks very promising. It looks like that's a big drop-off in areas that are quite badly affected by red needlecast. And that suggests that, once we have enough data to fit these regression lines, we should be able to clearly identify these deviations from the trend line. In the meantime, as we wait for more data to come in, we're now working quite actively with the forest protection team, and we're trying to implement some Sentinel-2 based inference into the Healthy Trees, Healthy Future framework that Ralph will introduce in a minute. In particular, we're hoping to repeat this analysis and try and screen some of the areas that are in the forest health database, and potentially to extract some of these spectral values and see if they add any value to these predictive models that the forest pathology team are developing. We're also continuing our broader remote sensing research as well. So we're looking at things like using aerial imagery and oblique UAV imagery to help score things like Stewart's copper spray trials there as well, and a range of other activities to just try and integrate this remote sensing technology more closely with the forest health research that we're doing at Scion. So I just have to acknowledge the tremendous support we've had, not just from the levy as well for funding us, but specifically to Mike Baker from Hancock Forest Management, who's entertained an enormous number of requests for forest permits and forest information, and for Interpine Innovation, who have helped us with some of the data acquisition tasks there as well. Thank you very much.